and stuff back. Alright, here, alright. Everybody turn one in or half one?
What's wrong with that? It's really short, so.
It's okay, it's really short.
Yeah.
This one's not super surprising on how short it is. So what we were doing, or what you were tasked with, was calculating the percent change. So what number are we? 12. Cool, only what, 23 more to go? Okay, so what you were charged with was calculate percent change in energy in a 1D particle in a box. In its ground state. So when we say ground state, what do we mean? What's our, yep, n is equal to 1. So we're talking about its ground state. If we increase the box length, box is increased by 10%. Okay, what was the equation for energy for a 1D particle in a box? Particle on a line, depending on who you talk to. So E was equal to what?
M squared.
Yep.
H bar squared, pi squared.
400 something.
Yeah, what was on the bottom?
2m squared.
Yep. Yep, so N, principal quantum number, constants, M's a mass, A.
That's the length.
Yeah, it's the length of the box. Okay, so what do you suspect should happen to the energy as we make the box longer? Yeah, energy should get lower, it's in the denominator. So what we're gonna do, we're gonna set up a situation, how are we gonna define the length of our box? Yeah, okay. So we have A is the original, what about when we increase it by 10%?
1.1a.
Yeah. That's the hardest part, right? Okay, now we have to set up a ratio. So we're looking at the percent change, right? The energy increase, energy of original. So what we find is okay, we have 1 squared, h bar squared, pi squared, all over 2m, 1.10, or a squared, all divided by a squared, right? What's going to cancel out?
Whole lot of stuff.
Yeah, a bunch of junk. And what we're left over with is basically 1 over 1.10 squared, right? So you can do the math, you can figure that out. If you didn't do it exactly this way and you found another, like another way to represent that, like if you took the difference of these two, that's fine too. Doesn't really doesn't really necessarily say if you had to find, I had to find the percent change, so I guess I should have subtracted the two. What'd you guys find for that though?
17.4 or something.
17.4%?
Maybe.
Okay.
Right.
Yeah.
It's whatever 1 divided by 1.21, and then I did 100 minus that.
Okay.
Just for change.
Yeah.
It's like 83% of the original value.
Yeah. So it has a significant consequence though for just changing something that little bit, right? Okay. So just one of the example problems that we have. Just wanted to test you on something more with particle in a box essentially. What were we talking about last time?
Transmission.
Yeah, we were talking about transmission, basically tunneling of particles. And we derived equations to get to that point, and we figured out how can we calculate the percent transmission? And what we're really talking about is in particle in a box, we set up a system where, how do we set our potentials? This was 0, that was A. What was the potential on this side?
0.
Oh,
yeah.
Well, that one is infinite. What's it in the box?
0.
Yeah. Outside of it?
Okay.
Infinite. Okay. And we added the qualifier that, what about these walls? What do we know about these walls?
Potential equals 0 at the wall.
Yep, they equal 0 at the wall, so they were impenetrable. We couldn't break them open. However, in most cases, we can't have a system like that. We can't have something that's infinite. So let's say we just have a constant. These are just really large. Okay, like that. And what actually happens is if you look at the wave function, originally in particle in a box, it went from 0 to A, right? But as soon as we start looking at a finite system, I should have drew that a little bit better. You start getting some of the wave function outside of the box, and even so, like if we looked at the electron density distribution or the probability distribution, we would see that there's a little bit of a probability of finding the particle outside of the box. So what consequences does this have for nature? Well, we've already seen one example. I showed you guys that scanning tunneling microscope where you can use electrons to transmit across like a really thin barrier. So you have an STM tip, you apply a potential, and what happens is depending on what way you apply that potential, you can either get electrons to shoot that way or go the other way. And this results in the visualization of these molecules. So, to show kind of an example of that, if I can actually get this thing, there we go, it's taken on. Now we're to the point where we're trying to visualize single individual molecules or even atoms on top of the surface. We can do that pretty well. The biggest issue is actually temperature effects. So if we could get really close to absolute 0, the molecules wouldn't move so much and we could get really clear resolution of them. But the problem is there's always a little bit of motion, right? Why is there always a little bit of motion?
Because we can't get to absolute 0.
Yeah, one, we can't get to absolute 0. And what else do we know about quantum systems?
Can't know how fast things are going if you're looking at it.
Yeah, you want to know where it is. If you're getting an idea, a distinct position, essentially, it's going to start moving a lot more, so the resolution is going to be worse. So what these little blobs are, they're actually 4-fluorostyrene molecules. The kind of an interesting thing is on copper, when you have a low coverage or a low amount of molecules on the surface, you end up having 3 of them that aggregate together in trimers. Then when you go over to gold, they end up aggregating into tetramers, or 4 of them. So there's a lot of weird stuff that's going to happen soon where we're looking at these metal surfaces which are used for catalysis and have really important applications in terms of producing chemicals and fuels and things like that. We're going to find out a lot more in this region soon. The other spot you guys know, but probably aren't aware of, that tunneling occurs is with proton transfer. So we're going to do some math today. We're going to show this is the probability of this. What each of these guys are, or what this is, first off, is called a molecular dynamics simulation. It basically uses quantum mechanics at different times throughout time to see what happens to a system. So each one of these frames that we're going to see is the result of a different quantum calculation. What these kind of pink spheres are, those are silver atoms. Red, or what atom do you think? Yeah, oxygen. I don't know why I picked blue, but blue is carbon. and then the little white ones are hydrogens. So what's going to happen is we're going to start seeing them wiggle around. And you can see that some of them, like that one just transferred, that one went back and forth. And you can see this one kind of bopping around, but this is the result of tunneling. So it's only because the protons can actually tunnel out of their potential that proton transfer happens and hydrogen bonds are so strong. It's a result of this weird quantum effect that happens. Ooh. But I always like this one because it's weird. You watch this one, it gives up like all of its protons, and it's just weird that something like that can sit and exist that way. But they actually do different sorts of vibrational measurements with lasers and all sorts of crazy stuff. There's a guy at Cornell that's trying to answer the question, is proton transfer like a concerted mechanism, or is it a one-by-one step, or is it a combination of both? So what I mean by that is, turn off, yes. If you look at proton transfer, is it, like let's say we have oxygen A, oxygen B, hydrogen, like that. Is it that this hydrogen just goes over there and we get minus plus like that? Or does it happen where it's like some sort of quasi thing where we get, and then this would happen again, this one would give up a proton and it would go to another spot? Or is it more like so, and that one would give off. And we don't really know that about water, which seems kind of ridiculous because we use it so frequently, but we don't actually know that. So there's a lot of weird quantum stuff that can happen. There's also protons that can transfer in different rearrangements. I'm sure Dr. B knows a handful of them. I tried to find some that were easy enough to explain, and I couldn't find any mechanisms that I felt comfortable being able to explain.
So that'd be like just hydride shifts and stuff?
Yeah, hydride shifts are an example of that, where they actually do tunnel. So what we're going to do today, we're going to go through a couple of problems. We're going to see what is the likelihood that this can actually happen. Okay, so let's first consider a proton, an acidic molecule. So, all proton, acidic hydrogen is confined to an acid. And we can represent the acid as a potential barrier. Acid can be represented as a potential barrier. With a height of 2.000 electron volts and a length of, let's go with 100 kilometers. We want to determine the probability that the proton can escape. energy of the proton is 1.995. Holy cow, long problem. Also incredibly warm. Got a lovely noise out there. Okay. Jeez. We have a lot of information there. What's important to us, or what do we need?
Probably the three numbers.
Yeah, 3 numbers are most important. We're a PCAM after all, right? Yeah, okay. So what are each of these numbers? What equation do we want to use? Or what are we looking at?
Guessing we're probably going to do the part of one box thing.
Could do that. We're actually not going to do that one for once.
Is it a T equation?
Yep, that's the T equation. So this is the transmission. So we're talking about the escape from that. So we're talking about transmission. So let's start with the original big ugly one, and we'll see if we can approximate to the simple one. So the big ugly one is 1 plus e k prime x plus e minus k prime, I'm sorry, that should be a subtraction. Minus k prime x, all that squared, all over 16 epsilon 1 minus epsilon, all that raised to the minus 1. Okay, so we need to find some stuff in here. What's what? You remember what epsilon was?
The ratio, isn't it?
Yep, it's a ratio. What's it a ratio of?
Energy
Mm-hmm.
over voltage.
Yep. Okay. We have both of those things. What's our energy? Yep, 1.995 eV. Then we have, what's our potential?
2.0.
Yep. Okay. What are my units of my epsilon going to be?
Nothing.
Yep, nothing. This ends up being close to 100%, 99.75. Okay, so we got epsilon, so we got a ton of stuff in there. What else are we looking for, or what else do we need?
K prime.
Yep. You remember how we found k prime? The square root of a bunch of junk.
2ME over
Yep.
H squared.
Uh,
Oh, I'm sorry. 2MV minus E. over-
yep. Yep, we got that. Okay, so we need our masses to, what should we get the mass in? Yeah, kilograms. So you can look that up for, we're doing a proton right now, so it should be 1.6 something, 7 times 10 to the minus 27 kilograms. You don't have to include that on your like sheets for the Quizlet. I'll give you that sort of stuff. Okay. Right. So then we have V minus E. If we do that, what's the value that we get?
0.004.
Yep, unit.
Quadruple.
Yep. Okay, so what do we got to do to that, do you think? Yeah, we got to get into joules because that's just the SI unit. So anybody know the conversion factor for this?
Is it electron? Chargeable electron?
What's that?
Is it chargeable electron? To get joules? What now?
I think so. 1.602 times 10 to the minus 19 joules per 1 electron volt. I think that's a coulomb,
Yeah.
or elementary charge of a particle. Okay, and then we got to divide this all by h bar. So you can look that up too. So 1.00 or 0.055 times 10 to the minus 34. Do you remember what the unit is?
Joules times seconds.
Yep. We got to square that. When you do all that, what you get as a result is 1.550 times 10 to the 10. Anybody have any idea what units you're gonna get out? Nope, seconds aren't gonna be in there.
Joules.
Joules aren't.
I don't know.
When you start breaking down the joules into their SI units, what you'll find is you get meters to the minus 1.
No, no.
If you break them down, you can see it. If you want to do it, we can do it. If you trust me.
I guess it makes sense because X has to be length up in there.
Yeah, exactly. And we want this to be, we want these two multiplied together to be dimensionless, right?
Oh, right.
Yep. Okay. We're almost there. Now the question is can we use the simple equation? Could we use, instead of doing that big long ugly thing, could we just do this, where we have 16e1 minus e x? Can we do that?
Yes. No.
Our length is too small.
Okay, so what do we have to show then? Or how is this one applicable? Or can we use this one?
X is much greater than
Yeah, so we have to have k prime times x has to be much greater than 1 to use this. Let's see what we get. So we got 1.550 times 10 to the 10 meters. And what was our x value?
100 feet.
Yeah. We gotta convert that to meters though. You remember how many those guys for every 1 meter?
10 to the negative 12. I mean, 10 to the 12.
Yep, 10 to 12. Could have negative 12 up top, whatever we want to go through it. I can do that. What you get is just 1.550. Nope, we can't do it. It's pretty close to 1. So now we have to jump back to this transition, or this tunneling probability. So we do that. Now we can just start plugging junk in. So 1 plus e to the 1.550 minus e to the minus 1.550. Square root all that. 16. What did we calculate epsilon to be? It's right in front of me. It's right there. Okay. 7.5. And then we had to look at the subtraction of those two. So 0.00. All to the minus 1. Okay. Everything should be unitless right now, which it is. That means it's a good thing. The answer we get 0.001967. If we want to convert that to a percentage, 0.196. That seems like a really small amount, right? Seems like it wouldn't actually ever happen. It rarely happens, but we still observe it happening for most of the systems that we look at, right? Like when we consider an acid, we can see it plucking some of those off. In this case, this would be a weak acid, but it still happens. This actually has kind of an interesting consequence. This is like if I took this eraser and I were to throw it against that chalkboard. And if I were to do that an infinite amount of times, one of those times, there is a likelihood that this eraser would go through that wall. If you did it an infinite amount of times. Maybe after like smacking it so many times, you break your eraser, you break the board, but there might be one point in time where I actually throw this and it goes right through that board. Which would be really weird. It makes me wonder about ghosts and things. Is that what's going on, or is it just people acting crazy? Okay, so let's look at a different example though. So in scanning tunneling microscopy, we look at electrons tunneling. In this case, we looked at a proton tunneling. Let's check out an electron. So we're going to have almost the exact same setup, except we're going to consider a semiconductor, and we're going to look at an electron in this case. So we can do the same thing. For semiconductors. Can anyone tell me what a semiconductor is?
Sort of conducts everything.
It sort of conducts. Yep, so it sometimes transmits electrons. We're going to talk about valence and conduction bands later in inorganic and later on in lab today. And the consequences that has for something behaving as a metal, not metal in a metal way. So have you ever seen like these things? Or did you ever really talk about that in Gen Chem?
Yep.
Okay, what these boxes are, that's where you have a ton of molecular orbitals, like in a solid, where they just start building on top of one another. What we're talking about right now is okay, if we have a potential barrier along here, what is the likelihood an electron can jump from this point to that point? If it can do that, you end up having a semiconductor. This is an example of a metal because the valence and conduction band are touching one another, and it allows the electrons to freely flow between a bunch of energetic states. However, in this case, what you have to do is, you know how you make a semiconductor behave more metal-like? Like what experimental conditions you have to have? If you actually heat it up a little bit, what will happen is some of these electrons will move up to the conduction band. What about this one? What do you think that represents? Yeah, nonmetals. So that's where electrons don't get transmitted, and that's because this potential is way too large, and the likelihood of an electron going from there to there is very minuscule. So what we're going to do is we're going to look at the exact same setup. We're just going to change our mass of the semiconductor. Then we're going to see something interesting. Okay, so example, suppose the junction, which is a fun word to say, between two semiconductors. Can be represented by a barrier height 2.000 eV and a length of 100 gigameters. Calculate the probability of an electron of energy 1.995 eV can tunnel through the barrier. So the ability for that to jump up. Okay, that whirring has stopped. We're going to open more windows. I am boiling alive. I don't know about you guys. James, can you open that one for me? I am not looking forward to summer.
Yeah, like yesterday was too hot at some points, I'm not gonna lie.
Well, when you're used to like negative temperatures outside, to suddenly jump up to 70 degrees, it's like, oh, I'm just sweating through everything. Why? Okay, so we're basically just trying to get the transmission again, right? All right, let's see, what can we do? Well, the only major thing that's really going to change out of all of this is our value of k, right? Because what's changing in this expression? Yeah, the mass is going to change. So let's calculate k, or k prime, excuse me. So you do that, 2mv minus e all over h bar squared. All we have to do, we just have to plug in the mass for an electron, so 3 times 10 to the minus 3, 1 kilograms. So it's much less massive. We're going to do the same sort of thing here, where we have that 0.5 eV, we have to convert that 0.5 eV into joules, so it's 1.602 2 times 10 to the minus 19 joules. All divided by h bar squared is 1.055 times 10 to the minus 34 joules times seconds. Add that all squared, what that ends up working out to be is 3.621 times 10 to the minus 20, positive 27 reciprocal meters.
Is that positive 27?
That is positive 27. Sorry. Yep, positive 27. All right, everything else is essentially the same. However, do we have to use this big clunky equation in this case? No, because if we look at k prime times x, you should get a value of 3.62 times 10 to the 15th. And again, there are no units on that, right? So way larger than 1. So we can approximate this to 16 epsilon 1 minus epsilon e to the minus 2 k prime x. When you plug everything in for that, what you end up with is 0.881 or 88.1%. So this is a very likely event then, right? Why the major difference? What's that?
Electrons are tiny.
Yeah, they're tiny. Their mass is much, much less. So if we were to consider, like, we have our potential here. And we have our wave function. If we were looking at a massive particle, a really massive one, we'd expect the wave function to die out pretty quick. It might not even make it to this point, or there might be a little sliver that gets over that point. What would you expect for a non-massive particle, though?
Just gonna go right through.
Yeah, it would do whoop, and then it'd start acting like a wave. Everything's waves. That's all it is, right? So what we found here is that depending on the mass, tunneling is much more important. It's a way more important influence for electrons than it is for protons, but it still has physical consequences even for protons. And they're starting to find that there's a lot more evidence for proton tunneling and things that we didn't think that they were actually going to be able to tunnel through. So now we have a couple of weird things. We have quantization, we have the effects of tunneling, so things can just go through stuff that they aren't meant to now. Let's see what other weird stuff we can find. How are we doing on time?
Well, not bad.
Okay, let's transition to another system. So we've looked at tunneling, we've looked at particle in a box, but what's kind of crummy about both of those systems?
Not really, is it?
Yeah, not not really realistic, right? We're talking about a particle bopping on a line, like going from here to here. We're only talking about one dimension. Let's bump up the number of dimensions. Let's get to a three-dimensional system. So the next thing we're going to discuss is particle in a box, a 3D box. Ooh.
Is particle in the 3D box going to be a particle that's not?
No, it is not.
It is particle in the 1D box.
Particle in a 1D box and stuff on tunneling. Those are the only two things you're going to have to worry about. We're not going to have enough time to go through all of this, so don't worry. And there's also some interesting consequences that come out of this too, that we're going to see. Okay, so we're going to consider a quantum system where we're going to be containing our particle in a box of length A in the x direction, length B in the y direction, and then length C in the z direction. Alphabet, it's good. All right, so let's consider quantum system, so quantum mechanical system. Contained in a box, length A, a width of B, and height C. We want to make our system even easier to study. What other things should we do? So right now, X, Y, Z, so we have a particle, we want it to be confined in that box. How are we going to do that?
Infinite potential everywhere else.
Yeah, everything outside of the box is an infinite potential. So the potential equal to infinity outside of the box. There's one more thing we should do.
Make it zero inside the box.
Yep. Actually, two more things we should do. E is equal to 0 inside the box. And we need one last parameter, I guess, or one last qualifier. It has to deal with what we were talking about electrons tunneling. So what do we want to assume about our walls?
So potential is also zero.
Well,
They're impenetrable.
yeah, we want to say they're impenetrable, so we can't go through those. So walls, box, are impenetrable. Is it in or in? Impenetrable.
It doesn't sound right.
Doesn't mean
I like
every.
the N.
Yeah, all right, we'll go with that. All right, let's consider what the Schrodinger equation is going to look like. Because if we know that, then we can predict the wave functions of each of these things. So
It's N.
it is an M? Ah! Impenetrable.
No. So it's like impossible.
So we got the Schrodinger equation. So for our system, we're always going to have that negative h bar squared over 2m. What do we have otherwise?
Partial derivative probably.
Yep, partial derivative when we were talking about a one-dimensional system, we had partial derivative with respect to x, right? If we're in 3 dimensions, what do you think we're gonna have to do?
All of them.
Yep, all of them. Y. Psi, x, y, z is all equal to, what should it equal on the other side? Yep. And then what else do we need there?
The same function.
Yep, same wave function. Okay, we have to do that. What we're gonna do though is we're gonna assume we can separate the variables. We should be able to, just because these are all based upon just positions, so we're gonna separate these variables out. So we separate variables. What we're gonna say is okay, we have our wave function that depends on x, y, and z. What we're gonna do, we're gonna split those up into individual wave functions, one that only depends on x, one that only depends on y, and one that only depends on z. So we'll call this one big X, I'm gonna try to make it as fancy as I can. Only depends on x times y. Try to make it as fancy as I can. Z or Z, depending on where you're from. I never liked Z. So, when you guys come back from break, we're going to look at that and we're going to try and decipher what we can out of these. What you might be able to expect is these just end up being the same thing as particle in a box, just in a couple different dimensions. Okay, are there any questions about what we talked about today? No? Tunneling's weird. It has important consequences, especially in electronics. You guys might have you ever heard of Moore's Law? Okay, what Moore's Law states is computing power is going to keep growing at an exponential rate, but we're at the point where we've actually made electronics so small that we can't make them any smaller because the electrons just start to tunnel out of where we want them to. So that's why we're starting to look at quantum computers and try and find new ways to build capacitors, which essentially electronics are all built off of, but it has to. We've reached a limit where we're actually too small to keep doing any better. All we end up doing is just throwing more and more of these capacitors on top of something to make it stronger. So the next bit of technology or processing power that we're going to have to do is going to have to move to either quantum computing or find some way to make electrons not tunnel, which I don't think is possible at all. So just something to think about. All right, I'll see you guys later on this afternoon.
You need goggles there, right?
You do not need goggles.